Now that you've watched the other videos relating to buoyancy and flotation, we're going to look at it from a mathematical point of view. First of all, you know that every object that is submerged has a buoyant force acting on it that's due to a difference in pressure from the top and bottom of that object. So if we have something here like located underwater, it's going to have a buoyant force, and that buoyant force is going to act directly up. What you know about this is that the amount of buoyant force that we have depends purely on the volume of the object. The buoyant force depends on the weight of the displaced fluid. Okay, so for instance, if this rock were bigger, it would displace more water and have a bigger buoyant force. To look at that mathematically, we're going to kind of derive a little expression for the buoyant force here that would be the weight of displaced water. And weight, we know, is mg. But instead of talking about it in terms of m, the mass, let's do it like we've been doing. We're going to look at it and talk about the mass of the fluid as being equal to the density times the volume. So in this case, I'm going to put some little subnotations on here. I'm going to say that the buoyant force is equal to the mass of the displaced water times g. And so that's going to be the density of the fluid. I'm going to put a little FL down here to remind us that it's the fluid, the volume that's displaced, and g. So this little expression here will cover us when we talk about the buoyant force. Now the displaced volume, you have to understand that's not necessarily the volume of the object. If the object were only partially submerged, like up in this case, the displaced volume would be this volume down here that's actually underwater. So you got to be kind of careful when you use this expression. It's not always the volume of the object, but if something's completely underwater, then that displaced volume is equal to the volume of the object. If I put this object underwater, depending on what it is, it's going to sink or float. And whether it sinks or float depends on the relationship between these two forces. The up force being the buoyant force and the down force being the actual weight of the object. So the weight of this object will help determine this. If the buoyant force is bigger than the weight of the object would float back up to the surface. If the weight of the object is bigger than the buoyant force, then it'll sink. If they're equal, it'll remain neutral and just float in place. I'm going to express the weight of this object similarly to the way I express the buoyant force. Instead of saying it's the mass of the object times g, I'm going to say it's the density of the object times the volume of the object times g. And we'll see that this is kind of going to help us find a convenient mathematical way to think about buoyancy. At this point, I know that the net force acting on this would be equal to the up force minus the down force, which would mean that it would be the density of the fluid. And since this thing's completely underwater, this displaced volume is equal to the volume of the object, and the weight will be the density of the object times the volume of the object times g. So that's my net force. If my net force, I'm going to actually factor this a little bit further, and I'm going to get an expression that says the density of the fluid minus the density of the object times the volume of the object times g. So if you look at this little portion here in the parentheses, if the density of the fluid is greater than the density of the object, then you'll have this expression will come out positive, which means our net force would be up, and this thing would float back to the surface. So in other words, if the density of the object is less than the density of the fluid, it'll float to the surface. If the density of the object is greater than the density of the fluid, then this expression will come out negative, and this thing will have a negative net force, which means it will be pointing downward, and it will sink to the bottom. So what this shows us mathematically is that floating and sinking depends on density of the object. If you have water, for instance, anything that has a greater density than water will sink in water. Anything that has less density than water will float in water. Let's look at two situations of equilibrium. Let's first look at the situation where an object is in equilibrium resting on the bottom of a fluid-filled container or an ocean or a lake or something like that. If this object's resting on the bottom, we know that it has weight and that it's probably made of something, well, it has to be made of something that has a density greater than water. And so its weight is going to be down here. If that's the case, that means the buoyant force acting on this object is going to be less than the weight. And so if I write the buoyant force, this doesn't seem to be a situation of equilibrium. We've got an up force that's less than the down force. So how are we going to make up for that and make it so this thing can actually be in equilibrium? Well, we need more up force. And what would be pushing up on the bottom of this thing? A normal force, of course. Okay, so a situation like this, let's say you're asked to find the normal force. How hard is this object being pushed up on by the bottom surface? Well, what you could do is you know that these things are in equilibrium, so you know that the normal force plus the buoyant force must equal the weight. This normal force would then be equal to the weight minus the buoyant force. Now, you might remember from the other video that when you take the weight and you subtract the buoyant force, you also get this thing called the apparent weight. I'm just going to write a little APP here. Apparent weight. Okay, the apparent weight is what an object would appear to weigh if it were submerged in a fluid. Okay, so let's say there was a scale on the bottom of this, whatever it is, it's called a fish tank. If we had a scale down here and we were to put our box up on top of that scale and weigh it, we would see that it would weigh less than it does if it was up in air, because it's being helped out by the buoyant force. That scale reading, which would be the same as the normal force, would be the apparent weight. So if you're ever asked to find the apparent weight is equal to the actual weight of the object minus the buoyant force. So that's one situation of equilibrium. Another situation of equilibrium would be if you have an object that is floating on the surface. This object is in equilibrium because it's not rising, it's not falling, and that must mean that the upward force acting on it, its buoyant force, must be equal to its weight. The reason that this works is because the amount of displaced fluid here is not equal to the entire volume of the object. So the volume of displaced fluid is less than the volume of the object, and that makes sense because this must be an object that has a density that is less than the density of the fluid. Otherwise, it wouldn't be floating on the surface. An expression for the weight would look like this, and the expression for the buoyant force, this is where we again have to be careful. This time, the volume that's displaced and the volume of the object are not equal to each other. There's less volume displaced than the volume of the object. That's how these are able to be in equilibrium. A very typical question might be, well, what percentage of this thing is underwater? If we have a situation where it's floating on the top and it's in equilibrium, we can say the buoyant force equals the weight. So we can say that the density of the fluid times the displaced volume times g equals the density of the object times the volume of the object times g. G is not going to matter too much here, right? We've got it on both sides. Now, if I'm talking about the percentage of this thing that's submerged, I'm basically talking about a ratio of the volume that's underwater to the whole thing. In other words, if I solve this thing for the ratio displaced volume, which is smaller than the total volume, that will be a percentage. And you could see in order to do that, I would divide both sides by VO, and I would also divide by both sides by density of the fluid. And I get this expression, that this percentage is equal to the density of the object divided by the density of the fluid, which is going to be a number less than 1. So then if we multiply it by 100 at the end, we'll get an actual percentage. That's why you can say things like an iceberg only shows the top 10% of its volume. And that's because the ratio of ice to salt water works out to be about 90%.